All right, so here we go. So today we're going to learn about rotational inertia and rotational kinetic energy. We learned about rotational inertia last year when we did torque. And you might remember these guys, right? Okay, we saw a few sheets that looked like this. There's this one and there's this one. All right, and so the idea was it basically is a measure of how hard it is to change the angular motion of an object, right? And so the idea was when you put torque on an object and try to rotate it, what we learned was that the angular acceleration of the object is equal to the net torque divided by the rotational inertia. Okay? This year we're going to approach it a little bit differently, and we're going to talk about it in terms of the rotational kinetic energy. All right? So another thing we learned last year was this, that the rotational kinetic energy of an object is equal to 1/2 I times omega squared. So very similar to our traditional kinetic energy equation, which is 1/2 mv squared, right? So the idea is our mass is replaced by inertia, our velocity is replaced by angular velocity. All right? So anyway, so we're going to talk about rotational inertia, how to find it, and then what it has to do with rotational kinetic energy. Okay? So here we go. All right, so imagine this. Imagine a 0.06 kilogram meter stick sliding along a frictionless surface at 5 meters a second. Okay, we could certainly calculate the kinetic energy, right? So let's see. So we would go, oh, well, kinetic energy is half of the mass of the meter stick times its velocity, 5 meters a second. Don't forget to square it. And so you're going to get 0.3 times 25. I have that number written down somewhere. And it gives you 0.75 joules. Okay? So no big deal, right? Now, another thing that we might want to do is, instead of having the meter stick just moving through space, suppose we wanted to rotate the meter stick around its center. So suppose instead we did this. So here's our meter stick, all right? So what we're going to do is we're going to imagine a pivot point here at the middle, all right? And then we're going to spin it, okay? So that this point stays stationary, and it's going to rotate around. Okay, so this is my pivot point. It's my axis of rotation is the term that we'll use for that. Okay, and we're going to spin it around. Okay, and I've chosen to make it so that it spins with an angular velocity of 10 radians per second, because what that'll accomplish is, if we use v equals omega r, what that means is that our endpoints, the endpoints of the meter stick, will be moving at 5 meters a second. Okay, so that was why I chose 10 radians per second. Okay, so here we go. So what if instead we rotated the meter stick around the center at 10 radians per second? All right, so what you need to do is you need to imagine the meter stick as a collection of particles that span along its length, right? So, you know, you've got a particle here, a particle here, a particle here, a particle here, right? And so the idea is, because they have different radii, they're going to have different velocities, right? And the farther out you get, the faster the particle is going to move, right? Oh, we also need to consider these particles, right? Okay? So if we imagine this as like a nearly infinite number of particles stretched along the length of the meter stick, we'd have to sum up the mass times 1/2 mv squared, 1/2 mv squared for each of the individual molecules or electrons or protons or whatever along its length. And you would get this, right? And it would be a nearly infinite sum, right? Okay? So, So let's imagine that we could do that for a minute, okay? So we're going to take the sum of the kinetic energy of all of the individual particles, okay? So what we want to do, though, is we want to, because it's rotating, let's replace each of the linear velocities with angular velocities, okay? So all I've done between this step and this step is I just used our jumper equation. I said, all right, well, I know that velocity is omega times r. So I've just replaced that there, okay? So here, I guess to be clear, make sure you understand, this depends on where you're at math. All of these little i's here, they don't mean initial. So the i's are the index that you're counting from. So mass particle, the mass of particle 1 times the velocity of particle 1. Mass of particle 2, velocity of particle 2. And so often what you do is you'll go I equals, so you sum from I equals 1 to, whatever, infinity. It's not really infinity, but it's a big number, okay? So that's all these little i's represent, is the number of the particle that you're talking about, okay? All right, so anyway, so I've replaced v with omega r, okay? And then a little bit of algebra we can, square the omega, square the radius, and get this. I pulled out the 1/2. Okay? So, remember, we learned that rotational kinetic energy is 1/2 I times omega squared. All right? Well, look, all of the particles are going to have the same omega, right? And here's my 1/2. So this term here is my rotational inertia. Okay? So what you're doing is you're summing up mass times radius squared for each of the individual particles along the length of the meter stick, or whatever your rotating object is. All right? And notice, this is super important. This is a property of the object, right? Because it's going to be dependent on the mass of the individual particles that make it up and where they're at. Okay? And so it's called the rotational inertia. It is a property of the object, okay, and the axis of rotation, which we'll get to in a minute, all right? Okay? Sometimes instead of rotational inertia, professors will call this moment of inertia, okay, which I never liked that term as well. But so anyway, that's what that is. And then the symbol for it, obviously I've already used this a bunch, is capital letter I, okay? So to find the rotational inertia of an object, it's just this. You sum up mass times radius squared for all of the particles, okay? And then our rotational kinetic energy, I wish I had used RKE here. Our rotational kinetic energy then is 1/2 I omega squared, all right? So once you've got the rotational inertia, calculating the rotational kinetic energy is easy, but how do you find it, all right? Because this, summing this up over the length of the meter stick is not, sort of feasible, right? Okay? So anytime that you see a sum like this that is either infinite or nearly infinite, you should think integration, okay? And so these are sort of our targets as we want to learn how to calculate these, all right? And I'll be honest, on the AP test, usually, I think the only one I've ever seen is some of these easier ones like this, okay? Doing some of these other ones over here where you've got cylinders, I think, if I remember right, requires double integrals. I'd have to look it up. But yeah, I would be very surprised if we saw that. Okay? So anyway, so what we're going to talk about now is how to get these equations. Where do they come from? Okay? All right. So, cool? I guess worth noting, if you've got a point mass, the rotational inertia is just mr squared. Okay? Okay, so where do the equations come from? So this, as I said before, becomes an integral. Okay? So the rotational inertia is the integral of radius squared with respect to mass. Okay? So what we're going to do here is something similar to what we did when we found center of mass. Okay? We're going to use a little bit of a trick. So the idea is, I'm trying to integrate r squared with respect to the mass, right? So that doesn't work, right? We need to get our variables to jive. So we got to do a change of variable, all right? And so what we're going to do is this. The length of the meter stick is uniform, right? Or I'm sorry, the mass of the meter stick is uniform, right? It's all wood, so that means if you cut it up, any little chunk of it of the same size is going to have the same mass, right? So we can go back to finding our linear density, okay? So our linear density of our meter stick would be mass per unit length, okay? But it's uniform, so for any little chunk of mass I take per unit length, it's going to be the same, right? Okay? In other words, any 1 centimeter will have the same mass, okay? Or any 1/2 centimeter will have the same mass, etc. Okay? So what we're going to do is we're going to take this equation here that I just scribbled all over. We're going to take this guy here and rearrangeify algebraically to give us this guy. All right? Cool. And then what we're going to do is we're going to do a change of variable. Okay? So let's do this. So we got to do some calculus. All right? So here's the deal. So our meter stick looks like this. Our axis of rotation is at the center. All right, I'm going to use 2 letters here. Let's use L to represent the length of the whole meter stick, right? Because we know the mass of the whole meter stick, we know the length of the whole meter stick, so we can find our linear density, right? It would be what? Well, 0.06 kilograms was the mass. The length is 1 meter. So we could, if we wanted, say, oh, well, that's 0.06 kilograms per meter, right? All right, but we're not going to do that. But we could do it, okay? Now, I think that because our pivot point is here, I think it makes sense to do this. So let's call half of the length r. So r is going to be L over 2. R is L over 2, okay? And so what we want to do is we want to imagine a number line running along the length of the meter stick. We're going to use, instead of using the traditional x, we're going to use r, lowercase letter r, and here's our position is 0. So that means our position here is positive r, and our position over here is negative r, right? Okay, so we've got this number line that runs through our meter stick, okay? So what we want to do is we want to integrate this. So rotational inertia is the integral of r squared with respect to mass, okay? So I'm going to do a change of variable. So this, so what would I be integrating between? I'd be integrating between 0 mass and all of the mass, where capital M is the mass of the whole meter stick. Okay, so this is a lowercase letter m, and this is a capital M. Okay, so I'm going to do this substitution. I'm going to replace dm here. Okay, so this becomes the integral of r squared times m over L dr. Okay, so now I need to figure out what the range of my r is. Well, to get the mass of the whole meter stick, I got to start at one end and go all the way to the other end, right? You can't just go from 0 to r. That would only give you half of it. Okay, so you got to go from negative r all the way to positive r. So we're going to integrate between negative capital R and positive capital R. Okay? So, next step. Well, let's see. This L in here, we've got r's here and L here. So we know that L is just 2r, right? So I guess I'm going to do two things. Well, I'll do it in steps, because otherwise I'll lose some of you here. So break it up in steps. So here we go. Integral from negative r, capital R, to positive capital R, r squared. I'm going to replace L with just 2r, capital R. Okay? Now, this is a constant, so I can pull it out. So now I've got, I'm going to go over here where I have a little more room. So now I've got the integral from negative r to positive r. Oops, I forgot to pull it out, didn't I? M over 2r times negative r, positive r, r squared dr. Okay. So now we integrate this, right? So we're going to get m over 2r times the integral of r squared is just 1/3 r cubed, right? And then I want to evaluate it between negative r and positive r. Okay? Oh my gosh, lots of algebra. So let's see. So now I've got m over 2r times 1/3 of, well, let's see. The top one is positive r cubed minus 1/3 of negative r cubed, but this negative comes out and makes this a plus. So I'm going to get 1/3 r cubed plus 1/3 r cubed. That's 2/3 r cubed. Okay, and so look what happens. The 2's cancel out. This r cancels one of these r's, and so I've got m r squared over 3, or more commonly, 1/3 m r squared. Okay? And then if you wanted to, remember that r is just L over 2. So a lot of times you'll see this written in terms of the length of the whole meter stick. So it'll be 1/12 m times L squared. Okay? And that just by substituting r equals L over 2 into this first equation. All right? So there are two different equations for, oh shoot, that looks like a fraction. So here are two different equations for, two different equations for the rotational inertia of a meter stick about its center. Okay? Where this is R and this is L. Okay? So, and just to show you, look. Here it is, 1/3 mr squared, okay? And I'll be honest, the one I gave you last year, well, my first year teaching here at South, the one I gave out said 1/12 ml squared. But I like having them all written in terms of the length from the pivot point, okay? Plus it makes it, notice that these two give you the same equation, where r is the length to the end of the thing from your pivot point. Okay? All right, so we just figured out one of these things, so that's pretty cool. That was some cool calculus. All right, so, and Abbo, if you need more help with that, I'm happy to go over it with you in class. All right, so let's now find the rotational kinetic energy of our rotating meter stick. All right, so let's see. So I, for our meter stick, we just decided that that was 1/3 mr squared. So that's 1/3. The mass of the meter stick was 0.06 kilograms. R for the meter stick is half of the length, so 0.5 meters. And don't forget to square it. Okay, and so that gives you 0.005 kilogram meters squared is the units that we write our rotational inertia in. Okay, and so now we can find our rotational kinetic energy, right? It's 1/2 I omega squared. So it's 1/2 I times omega squared. And if you do that, it gives you 0.25 joules. Okay? So that is that. All right, now, the next thing that we want to do is this. What if the axis of rotation was not at the center? All right? In order to figure this out, you have to use what's called the parallel axis theorem. This is super handy, okay? The parallel axis theorem. All right? So it turns out that if you know an object's rotational inertia about the center of mass. In other words, so that your pivot point runs right through the center of mass. Okay? Then you can find the rotational inertia around any other point. Let's call it point P, by taking the rotational inertia of the center of mass plus m times h squared, where h is the distance from the point P. Here, let me write it this way. It's the distance between the position. Oh, shoot. Stupid thing. It's the distance between. I just did the same thing twice. That's embarrassing. It's the distance between point P and your center of mass. Okay? So h is how far you have moved your axis of rotation from the center of mass, basically. Okay? So if I want to take my meter stick, so what we just did was this. We had the meter stick like this, right? And we rotated it around that axis of rotation, and it rotated around like this, and we discovered that I was 1/3 mr squared, where this is r, right? So now the question is, what would happen if we did this? What if we took the meter stick and we wanted to pivot it around the very end of the meter stick, point P. So that's literally the end of the meter stick, so that it rotates around in a much bigger circle. Okay? So we're taking the whole thing and it's going to go around in a big circle. So the question is now, what is I? All right? Well, the important thing to notice is that the first one we found, this is the center of mass, right? Okay? And here we're moving our pivot point from the center of mass to this pivot point P, and the distance is, well, half of a meter stick, right? So for us, h is simply 0.5 meters, because that's how far we moved our pivot point from the center of mass. Okay? So let's do it generically. Isn't that the same as r, right? Because r is half the length of the meter stick, right? Okay? So here's what we get. So I, the rotational inertia about the end of the meter stick, is I about the center of mass plus mh squared. So let's do some simplifying here. So this is 1/3 m times r squared plus m times, we decided the h was r, right? So this is r squared. So I've got mr, so this is, yeah, okay? So you got 1/3 mr squared plus another 1 mr squared. That gives you 4/3 mr squared, right? But it doesn't really make sense to use r, right? Because, you know, we're taking this stick, and the whole, now our radius is no longer half of the length. Now our radius is the whole length, right? Okay, so let's call this L again. Let's call that 2r. Okay, and so what I'm going to do is replace r with the length of the whole stick. So if L is 2r, then r is L over 2. So I get 4/3 m times, instead of r squared, I'm going to have L over 2 squared, which is 4/3 m times L squared over 4. And the 4's cancel. And you get 1/3 ml squared, where L is just the length of the whole stick, right? So here, on the equation sheet that we use, I wrote it as r, but notice what r is. It's 1/3 mr squared, but here r is the length of the whole stick. Okay, so I just changed my L back to an r. I just switched the letter around. Okay? So, and that's exactly what we did, right? That's the rotational inertia of a meter stick about the end, right? Okay, and we found this by starting here and then using the parallel axis theorem. Okay? So, I think that's everything. Is that all I got for you? Oh, okay. Oh, yeah, so here's the last thing. All right, so suppose we had a point particle traveling in a circle, and we wanted to find the kinetic energy of it. All right, so here we've got a 10-kilogram object moving at a velocity of 5 meters a second in a circle with a radius of 4 meters. Okay, so we've got this thing just like going around in a circle with these conditions. Okay, so let's do this. So one way you could consider this is you could say, okay, this thing is moving. It's got kinetic energy, right? Okay, so let's figure out the kinetic energy. So, so to consider this energy, so we'll do option 1 in red. So option 1 would be to look at the kinetic energy. So you just do 1/2 mv squared. So half of 10 kilograms times our velocity, which is 5 meters a second. Don't forget to square it. So that gives you 125 joules. Okay? So that's one way you could consider it. So the total energy of this thing, assuming that it's got no height and nothing stretchy or anything, is to say that it's got a kinetic energy of 125 joules. All right? But what if I just wasn't, maybe I wanted to think about this a little bit differently. Maybe I wanted to think of this as a point particle that's sort of rotating, right? Technically it's not rotating, it's, you know, revolving in a circle. But, you know, I mean, I guess maybe you're thinking, oh, well, it's on a string that's massless maybe, and, you know, so this whole thing is rotating. All of the mass is concentrated up at the outside edge, right? So another way you could do it, option 2, would be to consider, instead of, you don't consider both, it would be one or the other. Option 2 would be to look at the rotational kinetic energy. Okay, so rotational kinetic energy is 1/2 I omega squared. Okay, so let's take a second and calculate this. All right, so remember, I for a point particle is simply mr squared. So for us, it's a 10-kilogram thing. It's going in a circle with a radius of 4 meters. Don't forget to square it. This gives you 160 kilogram meters squared. Okay. But I also need to find my omega, and omega is v over r by using a jumper equation. So for us, that would be the velocity, 5 meters a second, divided by the radius of the circle, 4 meters. That gives you 1.25 radians per second. Okay? So our RKE then would be 1/2 I, which we just decided was 160 kilogram meters squared, so we're 80, times omega squared, 1.25 radians per second. Don't forget to square it. And guess what? If you do that, it gives you 125 joules. Okay? So it's the same thing. So if you're looking at a point particle moving in a circle, you can consider its energy as either kinetic energy, traditional, or rotational. All right? And you'll get the same result. Okay? So there we go. That is it for rotational kinetic energy and rotational inertia.